Hello, good afternoon once again to all the participants, and we have reached session number 4 of today's. Hello, can, hello, Dr. Devajit, can
Yeah, your voice is breaking, Dr. Nanda.
okay, now it's clear, sir?
Yeah, it's better.
Okay, so I welcome Dr. Devajit Day on behalf of Department of Electronics and Communication Engineering, Madanpur Institute of Technology and Science. And sir, thank you for accepting our invitation to deliver a talk on your topic of interest, that is 5G and its beyond for sub 6 gigahertz. It is quite
Yeah,
a interesting topic, and I think participants will get some insight from your talk. I'd like to introduce our speaker, Dr. Devajit J. He is working as a senior R&D engineer in Test Technologies and currently posted in Hyderabad. Dr. Dev was born and brought up in Kolkata, West Bengal, and he started his engineering career and a BTech degree in electronics engineering in West Bengal. And then he completed his MTech with specialization of microwave engineering from VIT Misra. And his PhD degree he completed from NIT Raulkala in the year of 2018. And he has 2 years of teaching experience and in Institute of National Importance, and he has more than 7 years of research experience. His research experience includes academic, industry, and his research career also. Dr. Devajit is currently working as a senior research engineer in the R&D Center of Edge Technologies Corporation, which is a Korean multinational company and currently posted in Hyderabad. Dr. Dey has published more than 30 research articles in peer-reviewed journals and conference proceedings. So Dr. Dey has also received many awards from internationally reputed institutions and organizations in various technical events. And his current research area are base station antenna, phased array antenna, MIMO antenna for 5G and sub-6 GHz, Wi-Fi products, massive MIMO antenna, beam steering or beam forming antenna, conformal antenna, airborne antenna, so radar, metameter lens, mutual coupling, power divider, phase shifter, and radio detectors. So these are the core core research area in microwave engineering. So I think sir will give a very good insight about this topic. It's also includes of 5G and beyond sub 6 gigahertz. So once again, welcome sir, and I request you to share your screen and you can start, sir.
thank you, Dr. Nanda, for the introduction to the audience. It's my pleasure to give a talk in the short-term course. So I'm presenting my screen. Is it visible? Is my screen visible?
Yes, sir, it's visual.
Okay, thank you. So I'm starting. So today, as you know, already Dr. Nanda has given you the uh, topic name. This is 5G and it's beyond for sub-6 gigahertz. So these are the contents that today I'm going to discuss. The first one, I'll talk about the introduction of the different 5G layers, then how the mobile and wireless networks are used and evolved in the last few years and the coming years, and how we can improve the cellular networks, and then the massive MIMO, the massive multiple input, multiple output. What is the significance of this massive MIMO antenna in 5G systems? And then a brief ideas on few beamforming techniques, different beamforming techniques for 5G massive MIMO antenna. And then small cells, what are the small cells, what is the role, and why are going to use the small cells nowadays, and the conclusion. So yeah, the first thing is the 5G network layers. So from the diagram, what we can see is that, so generally all these 5G network layers are divided into three parts in a broad way. So first one is that large cells, or we can call it as a macro cells. So this is generally for the lower frequency range, sub 1 gigahertz. That means beyond less than 1 gigahertz, around starting from 700 to up to 1 gigahertz. So there we are using generally the macro cells, the large cells. The main thing is that here we are looking for the coverage. That means for up to maximum distance, what is the maximum coverage area, how much long, up to long distance you can cover. So that we are that generally macro cells are focusing on those coverage layer. And as the name suggests, that large cells, that means the size of the cells or size of the base stations are very huge if you want to cover more area. Okay. Next layer, which is coming under sub 6 gigahertz, starting from 1 to 6, which is covered by the small cells or macro cells. So generally, both of these type of cells, small cells or macro cells, can be used in this capacity layer. This is also known as capacity. So capacity layer. So what is the difference between coverage layer and capacity layers? In capacity layers, we are more focusing on the dense traffic. That means coverage is not the point which we are looking for, but we would like to give the importance to the capacity. That means obviously, that means the name suggests that more and more data traffic will be there in comparison to the coverage layer. So more users will be there in the capacity layer. So obviously, in that case, more densification is required, and hence we are using the macro cells or small cells. And next is that high throughput layers, where we are using the small cells, particular small cells. We'll also discuss that what is the small cells, and there are a lot of types of categories are there in the small cells. So mainly, if you see the high throughput layers, which is also known as, like we can say that millimeter waves, so starting from 26.5 gigahertz, and also like in different bands more than 6 gigahertz up to 100 gigahertz, we're using this high throughput layers. So here, this is mainly for the, we can say, the indoor applications, not purely indoor, like cafeteria or station or stadium, like where more people will be there, more wireless net uses will be there, huge traffics, huge data traffics will be there. In that case, we need to use the millimeter wave. So high spectrum bandwidth is required. So in that case, we are going to use the small cells. And there, obviously, you need a very high throughput of your communication. Otherwise, you cannot sustain so much of data traffic. So these are the brief three layers which we divide in the 5G. So now if you see the usages of wireless communication in last few years, so we can see that, so that every year, like more and more devices are coming. Also, you are aware of that more users are coming, and obviously as the devices are increasing, so data traffic is also going to be increased. So it has been observed that from Ericsson, they have published one report that in every year, like around 10% of devices are getting increased throughout the world on an average. More device, 10% more devices per every year, and 47% traffic data rate is getting increased in every year. So these are kind of statistical data which has been collected from many resources. And if you see the from 2016, if you see the first chart, the connected devices. So in 2016, per person, two wireless devices per person. That was the number of usages. But if you see in 2022, it has been estimated that each person will use around 3.6 number of devices, wireless devices. So you can see that how, like, throughout these 6 years, how that number of connected devices are getting increased year by year. And if you go to the data traffic area, so in 2016, 970 MB per month per person was used, but now in 2022 it has been calculated that around 9.1 GB, more than 10 times per month per person data traffic will be there in 2022, and obviously it will get more and more. So this, if you now, the next question will come, how we can like attain this huge data traffic, or how we can pay for this, how we can sustain, so that how our systems should be smart enough, or so that we can have this huge data traffic in the coming years. So the main thing is that we need a very high throughput in the 5G network. That is the main concern, that we need to have a high throughput in the 5G network. So, and obviously, whenever I'm talking about the high throughput, so all, because in the last like 4G or 3G or 2G, those LTE connections, there are many things that there are many devices are there which is not supporting those high data traffic. So then this IoT concept came. So where from those IoT and ultra reliable communications and many other resources, we can also create our revenue for the 5G systems. So those inter IoT things, those ultra level communications, those modern days devices can handle this huge air traffic. So now coming to the my next slide. So this is the, you can see is also an Ericsson data. So you can see that how the mobile traffic expanded. You can see that from 2014 to 2024, the 10 years. So in 2024, it is going to be around 130 exabyte. So I think that 1 exabyte is 10 to the power 9 gigabytes. So you can imagine, even we are not, even nowadays also we are not aware about this EB, that exabyte. Generally we work on that gigabyte or something like that. But exabytes, you see that like exabytes is a huge data traffic. So in 2024, it has been like predicted that around 130 Mbps, 130 exabytes per month will be used. So you can see clearly, you can see the curve how it is getting increased day by day. And from 2G to 5G and even the 6G, like you can see how the networks are getting evolved. So if you remember, like 2015-16, we see normal macro base stations, which is normal around like you can, those are for mainly for 2G, for 3G, those are sufficient. Okay. So but that was, as the data traffic are getting increased, that the single macro base station was not sufficient. So what scientists or engineers they have proposed more densification. That means just simply increasing the number of base stations. So in the second 2000, around 2016-17, we have used more number of base stations to densify the cells. So but more densification is also not the solution. That I will explain in my next slide. Why densification is also not the proper solution to handle the data traffic or to handle the more number of users. So then this concept came, the massive MIMO or digital beamforming. So in massive MIMO, yeah, we can access or we can give the services to many users in dense applications, or in also you can cover many coverage area also can be covered, capacity point of view also massive MIMO is a great success. In the coming years, we'll see more and more application in the millimeter waves also. Okay, millimeter waves, as I told you, we will have a lot of bandwidth will be more, so we can use millimeter waves for the, but not for the outdoor applications, mostly for the semi outdoor or semi indoor applications. The millimeter waves will come into the picture. Already in many countries they have already deployed these millimeter waves base station antennas. So that will be in the next area of research also, like how people are, many researchers are working on this millimeter waves nowadays. So these are the global footprint for the 4G, this LTE and the sub-6 gigahertz or 5G spectrum allocation. So one thing we need to understand, that 5G is not a pure separate technology compared to 4G. Okay. It's not a pure different technology. We can say that 5G is nothing but the advanced version of 4G. 4G will never absolute. 4G will be always there, but some extra bands has been coming in our systems, so which are going to be used. So that is the 5G. 5G is nothing but the advanced version of 4G. We can say in that way. 5G is not a totally different technology. That we have to understand. Yeah, so obviously some extra features has been added, but it's not a totally new technology. Yeah. So if you see that throughout the globe, but there are a lot of different in Europe, in America, in China, in Japan. They are using a lot of this 5G spectrum bands. So these are standard bands. In India, earlier we have decided that the Department of Telecommunication, that 2.3 to 2.4, which was the actually the LTE band, which is going to which are using nowadays for the LTE applications. So that was we also used for the 5G. But very recently, India has allocated a new band that is called from the C band, from 3.3 to 3.8 gigahertz for the 5G. So now from now onwards in India we'll be using this band 2.3, 2.4. As I told you, that will be also there, but the new band is 3.3 to 3.8, that is also going to be used in our country. And already those bands are already used in Europe. You can see that Europe is already started to use the 3.4 to 3.8. So band 41 is also band 41, band 40. This is already is in use in China. So these are brief of footprint of the LTE and 5G bands. So mostly I'm talking about the sub-6 gigahertz bands. So now the next topic is that, okay. So I talk about that, okay, how we have involved or what are the lacuna in different technologies. But the thing is that how we can improve a cellular network. That we have to understand. I was talking about the throughput is fine, but how we can actually increase this throughput if we like coming from 2G to 3G to 4G to 5G like that. So these are basic formula is there to calculate throughput. The throughput, one thing you have to remember that the unit of throughput is called bit per second per square kilometer. So it's nothing but the multiplication of three parameters: cell density into available spectra into spectral efficiency. The cell density unit is cell per kilometer square, available spectrum in hertz, and spectral efficiency is bits per second per hertz per scale per cell. So whatever the networks areas are there, generally it has been divided into two parts. Two-tier networks. So it is called two-tier networks. So these two-tier networks are then split into two parts. One is hotspot tier and is coverage tier. So in hotspot tier, what is the hotspot tier? So where high cell density is there, and that is for only for short range. That means I told you kind of semi-indoor, semi-outdoor, where we are going to use the millimeter wave. Why you are using to? Because in millimeter wave the electromagnetic waves cannot penetrate the walls, right? So outdoor to indoor application is not preferable for millimeter waves, but as we can have a wide bandwidth for millimeter waves, we can use it for semi indoor, semi outdoor, and also it can have the facility to accept very high cell density. That high cell density means data traffic will be more, densification will be more people, more users will be there to access the internet, their phones, their laptops. And generally, like, as I told you, for stadium point of view, you can think like in the cafeteria, in the metro station, where more and more people will be there. In a small area, but you need to have a more service. So if you go to the formula, that cell density, obviously, if you need to high, if you need to have a high throughput, either cell density or available spectrum or spectral efficiency has to be more. So in hotspot tier, obviously I told you the cell density will be more and available spectrum will be more, because millimeter wave we can have a lot of bandwidth. So this first two terms, cell density and available spectrum, will be more in case of the hotspot tier. In that way we can have a high throughput. In that case spectral efficiency is not important. Okay, we can have a moderate spectral efficiency, but first 2 points is the cell density and available spectrum will be more in case of the, if you need to have a high throughput in the semi indoor, semi outdoor applications, short range applications. Now, next thing is the coverage tier. Here, there's the reverse one. We need a large coverage. We need to cover more distance. So there, obviously, we should not use the high frequency. That means millimeter waves should not be used. We should use the sub. Mostly, we're using the sub 6 gigahertz bands, which I was talking about the 2.3, 2.4, or 3.3 to 3.8. Those bands we will use for the coverage tier. Here, obviously, cell density will not be more. Obviously, you can understand because large area will be there. Now, densification will not be there. So cell density will be less. Available spectrum will be less because it's like sub-6 gigahertz. We don't have sufficient bandwidth. So obviously, then I have to increase the spectral efficiency. So higher spectral efficiency is very much desired if you need to have a high throughput in coverage tier. So I hope I'm clear that in hotspot tier, we need to have a good high cell density and available spectrum to have a better throughput. And for coverage tier, the same is like to have a better throughput, we need to have a better spectral efficiency, because cell density and available spectrum we cannot increase. So only the spectral efficiency we have to increase for the coverage tier. So now the next question is that if you give more focus on the coverage tier, so obviously I was discussing that I need to improve the spectral efficiency. So how we can improve the spectral efficiency, and what are the limitations or issues in spectral efficiency? So here we're assuming one scenario. So I have four base station antennas. Four base stations are there. You can see that marked with like four blue color dots. So this blue color dot, each blue color dot means one base station. So there are four base stations are there. So, and this is the spectral efficiency which has been plotted. Four base stations, right? Four peaks we can see. But if you see that, suppose if the user is close to the base stations, so obviously it is he or she will get a better spectral efficiency, and obviously that will give a better throughput. But as you go away from the base station, what will happen? obviously you will have a less spectral efficiency because it is decaying. Spectral efficiency decaying as we move from the away from the base stations. Okay. So initially, to improve that issue, what people have suggested, let us densify the area. That means let us increase the number of base stations. So here you can see that instead of 4, we are using 16 base stations. So obviously, more peaks, you can see that 16 peaks are there for 16 base stations. So the thing is that, yeah, obviously the performance has been improved compared to this one to after this densification. But it has been observed that we are getting mediocre performance because again, if you increase the number of base stations, the spectral efficiency is decaying rapidly from base station to base stations. Again, the issue will be still there if anyone is like in between the one two base stations, he or she will not get proper throughput because of the less spectral efficiency. So densification is not the permanent solution or the best solution. Yeah, it has given some mediocre performance, but not up to the mark. And also, we cannot use higher frequency. That means we cannot use the millimeter wave for the coverage. Already I told, because millimeter wave cannot penetrate the wall. So obviously, for that we need a sub 6 gigahertz bands. So that's why cell densification is not the ultimate solution. Higher frequency is not a solution. So what we can think? What is the next thing that to improve the spectral efficiency? Here, what it has been done, that is, I kept the 4 base station. I have not increased the base stations. But what I did, or not me, by the coverage people, they have made for one base station, if you consider this is one base station, the coverage has been made more uniform. If you see that each base coverage for each base station has been made more uniform. So obviously, if you compare from this plot to the earlier initial plots to these plots, here also 4 base stations, here also 4 base stations, but the coverage is more uniform, right? So obviously, I'll have a more stronger signal. You can see that even if I move from one base station to another base stations, I will get very good signal even if I go a little bit far from the base station, because the coverage has been spreaded for each base station. The coverage has been spreaded for a large area. So obviously I'll get more better throughput. Okay, the spectral efficiency is more, and as you know, spectral efficiency is more. That means my throughput will be more. So I can so it's a system through which you can have a better throughput. Now the next question will come: how we can get this kind of plots? What is the things behind that so that I can get my coverage as uniform coverage from here to here? We can see these plots is fine, but how we are getting? What is the phenomena behind that? That my coverage is getting uniform, even from the single base station. They are the concept of massive MIMO or beamforming. Now, let us consider this first diagram. So here, this is the one single base station antenna, right? One single element is there. So it is radiating throughout its throughout the towards the users. So suppose there's one user is there, right? And M is number of antenna. So here number of antenna is 1, and there's one user is there. So my antenna is radiating. Now when this user is accepting the radiation from this antenna, obviously there are also multiple users are also there. They are also getting the radiation from the same antenna. So this radiation is cannot focused particular to this user. So obviously from this user to user number 2, 3, 4, there will a lot of interference will be there, because on a single antenna there, and it is radiating in all the directions. Throughout this direction is radiating. Here you can see the scale, right? Blue means strong signal, and yellow means very less signal. So you can see that obviously it is radiating towards the whole region. So obviously one user, many users cannot, a lot of interference will be there from user 1 to user 2 to user 3. Next step is that you can see that I have increased the number of antennas. Instead of 1, the single base station, I am increased the number of antenna elements. Now the antenna elements is 8. So my beam is getting much narrower. The antenna is radiating with much narrow beam width. So now, particularly this user is getting a straight beam towards the users, right? So obviously, my other users will have less interference from these users, right? But also, if you but there are substantial some side lobes will be there. These side lobes, you can see these are side lobes. These are main lobes. This side lobe will still create the issues, right? Interference is obviously it has been reduced, but still not up to the standard. So what we did, we have again increased the number of antennas. Now this you see that how the beam becomes narrow. It's just like a pencil beam, or you can call it as a laser beam, right? So each you can see this user is only getting the radiation from this beam. Even if I have a lot of other users are there, those users are not getting interfered from this beam, right? Obviously now the question will come, okay, this user is getting the radiation, then how, suppose there is another user, how this user will get? Obviously in that case I need to do the beam forming. First massive beam concept comes, and then how the beam forming can be applied to the massive beam, right? So obviously if you increase the more number of antennas, my beams will get more narrower, just like a laser beam or pencil beam. My antenna gain will be increased, because we know that if we need to have a array gain, how we can calculate? Single antenna gain plus 10 log of number of antennas. So obviously my antenna array gain has been increased. Okay, and also I was, and also the people have was able to reduce the less leakage, nothing but the this is about the side lobe levels. So the side lobe levels has been also reduced in the undesired locations. So wherever my users are there, only that direction the main beam will be focused. So the massive MIMO, full form, massive multiple input, multiple output. So there are few characteristics are there for the massive MIMO. So first cat is the many BS antennas. BS means base station antennas. So like if you see the M, I told you that M is the number of antennas. So here 200 antennas are there, and K has been referred as to number of users. So let us assume that the 40 users are there, and M is 200 antennas are there. For single base station, and there are 200 antennas are there. So obviously the massive MIMO antenna should have M should be greater than K. That means number of antennas should be more than the number of users. In that case, I can easily give the access to all the users using the beamforming techniques. Okay. So beamforming, I'll talk about the beamforming techniques later. So next is the high spectral efficiency. Already I told, if you go with the massive MIMO application, then my spectral efficiency coverage will be more. It will be more uniform. So I'll have a higher spectral efficiency, and that will give the many stimulus users, simultaneous users. We can give the access. We can give strong directive signals and very less interference. So actually, this concept, this massive MIMO, first was published by Thomas Marzetta in 2010. So it is a published one paper that non-cooperative cellular wireless with unlimited number of base station antennas. At that time, we may not be aware of this kind of technology is going to come, but nowadays, maybe in 2010, we never thought that okay, massive MIMO will be so much hot topic. But nowadays, you can see that we can't think about the massive MIMO if you have to have a very good performance in our cellular communication. So here, how we can deploy the antennas in massive MIMO for subspeakers. So let us take a real example. So here is a picture of a site. So here, these are some symbolic representation are there. You can check that this is one site. Triangle is there, which is referred to as one site. Okay. So this is, you can see that it can cover all the 360. If you consider three sectors, it is called three sectors. One site is having three sectors. Okay, 120, 120, 120. So that it can cover the whole region. Now each sector, so that means this is one sector, this is one sector, this is one sector. each sector 4 panels are there. Okay, 4 panels are there because this is my one panel. This is my one panel. You can see that one panel. So if I want to see what is inside of this one panel, I can see that. Okay, so there are 8 elements are there, and all these are dual polarized, or you can say cross polarized antennas. Okay? What is slant polarized? So cross means is like this is for one polarity, this is for one polarity. So here I can say that it's a dual polarized antenna. So 2 ports are there, right? You can see that one port for one polarity, another port for another polarity. So this concept was there in the LT. In LT, we that's one input or output per polarization. So this is if I say, so generally these polarizations are referred as plus minus. So if I say this is plus, so all the 8 pluses will be connected with this port, right? So this is my p polarity for one, and this is for m polarity minus. So again, m elements are connected with this port. Okay. So this is about the LTF. So 2 ports for 2 different polarizations. Okay. Now, so I can say, so if you ask, okay, sir, how many antenna elements are there? So I can, what I would say, okay, so there are 8 p polarity elements and 8 m polarity elements. Now, what what are the changes in massive MIMO? Massive MIMO has been designed in such a way that I can control each element separately. That means here, if I want to give the signal, input signal here, so I cannot treat this element separately because all these 8 elements are connected together. That means one common signal for one polarity. But here, what will happen? Polarity will be maintained, but I can control each element separately. So that means, let me show you that how we can calculate the number of antennas. I was talking about that we need more number of antennas. How we can calculate? So here, if you see that in each panel, I have 8p polarity, right? That means I have 8 elements because I can control 8 elements separately. They are mounted in an array position, but I can control 8 elements separately. So I have 8 elements, right? So in each panel, I have 8 elements, right? For single polarity. So here 8, here 8, here 8, here 8. So that means 32, right? So 32 polarities antenna elements are there, and another 32 for minus polarity, right? So that means, well, how much? 64. 64 antennas are there for 2 polarities, 32 for plus polarity, 32 for minus polarity. That means each sector is having 64. So how many sectors are there? 3 sectors, total 192. That means almost 200. So in this way, we can increase. You see, I'm not increasing the size. My size of the panel is same, but the filtering network is different. That's why, keeping the same size of the base station, I can install my massive MIMO antenna. Okay, we don't need to change. We don't need to increase the to have a more number of antennas. Okay, let us say initially I was having only 8p and 8m, but no, but actually we can increase the increase the number of elements effectively without keeping the same size of the site or the base station. So obviously, as I told you that it can increase the system capacity and makes system energy efficient. Also, massively increase the throughput and the capacity. Already, I think you have some idea. And as we use a large number of antennas, Massimo, there is an issue of interference. Obviously, there might be an issue of the interference from the port-to-port interference, may be an issue. So there are a lot of techniques out there how we can reduce this port-to-port interference. So here you can see that how we can reduce the beam width, or we can reduce the main beam width of the main lobe. So if we use the one radiating element, you can see that how the beam width is more. As I am increasing the radiating elements from 1 to 2, beam width has been narrowed. Now in 4, it is more narrower. So like this way, we can increase the number of arrays and we can have a less beam. Now, coming to the beam forming. Massive MIMO is discussed. Now, how this beam forming can be applied to the massive MIMO. So, if you see that beamforming, what is beamforming? The very basic definition of beamforming. Beamforming is a process and a technique generally formulated to produce a radiated beam by from the antenna by completely building up the process signal in the direction of desired terminal. That wherever my direction is there, wherever my users are there, what is the my desired terminal, desired directions. In particular, in that directions, my beam will be formed. My antenna will create the beam. That technique is called the beam forming. Even the name itself, we can from the name we can call it beam forming in a particular desired direction. Okay. Now, what are the benefits of beam forming? Same thing, like we can enhance the energy efficiency, we can increase the spectral efficiency, and system security can be also increased using the beam forming in massive beam. Now, generally, beam forming can be classified as four types: switched array beamforming, adaptive array beamforming, wideband beamforming, and narrowband beamforming. So first, let us talk about the narrowband beamforming. So this beamforming technique, this narrowband beamforming technique, is applicable when the input signal will have a fractional bandwidth of less than 1%, or very narrow. But very narrow band case, we use this narrowband beamforming. Okay. Now, generally, whenever see beamforming is total different topics to discuss. So I'll just talk about very initial points, a very brief point discussion. I'll do with the beamforming. So whatever the signals which will impinge on the antenna, okay, that or the input signal, that should have a very less signals of less fractional bandwidth. And obviously, we need to keep in mind that the bandwidth of the impinging signal should be narrow enough to make sure that signal received at the opposite end of the array are still correlated. That means from transmitter to receiver, both should be narrow band. Otherwise, this proper transmission will not happen. And generally, we use the Butler for narrowband beamforming. We use the Butler matrix for this narrowband beamforming. And what is Butler matrix? It's a kind of microwave network generally used for the beamforming and scanning networks for linear and circular arrays. And particular limitation is that only for the narrowband. But obviously, next question is if the beam width will increase, what will happen? When the beam width will increase, the bandwidth for narrowband is fine, but when the bandwidth will increase, frequency bandwidth will be more of the signal increase, the phase weighting some noise is coming.
Yes, sir, it's clear now.
Okay, fine. So as the bandwidth will be increased, the phase weighting computed, because all these beamformings are generally depending on the phase weight computation. So what are the phase we need to give for each element? You can see that a lot of antenna elements are there. What will be the phase computation, phase weight of each element that has to be computed? So if we increase the bandwidth, this phase weighting computed to steer the beam in a particular direction is no longer correct. So therefore, to generate a particular correct phase vector or phase weighting vector, we need a more complex arrangement for wideband beamforming. For narrowband beamforming, it's easy. We can simply get it from the beam Butler matrix. That is very easy to create this phase weight vector. But when it will be more, the bandwidth will be more, we need to have a complex arrangement. So wideband beamforming is acceptable when the fractional bandwidth of signal is up to 25%. And for wideband signals, each signal consists of, and obviously whenever we'll have a wideband signals, each signal consists of infinite number of frequency components, different frequency components. Because it's like wideband, each signal will have lot of frequency components. So obviously the phase values will be different from different frequencies. So we can have a lot of frequency components. A lot of frequency components will have lot of different phase weight vectors. So to accommodate those complex things, we incorporate another thing that's called TDL, tapered delay line. So what is the role of this tapered delay line? The tapered delay line which actually allows each antenna element to have a correct phase response that varies the frequency, because I told you that with the as you vary the frequency, the phase response will vary because it's a wide band. So obviously we have to compensate the error. So how we can compensate? Because lower frequency signals will always have the less phase shift, and the higher frequency signals will have a high phase shift. To compensate this error, and obviously they will for a same propagation distance, lower frequency is also traveling, higher frequency is also applicable. So to have a given propagation distance, or as they travel the same length, but lower frequency will have less phase shift and higher frequency will have higher phase shift, to accommodate or to compensate this error, this TDL or taper DL line has been introduced. And in that case, we cannot use this Butler matrix. We have to use the blast matrix. It is also another technique for the, and that is all applicable for wideband. It is more complex compared to Butler matrix. And in blast matrix, we use the directional couplers, we use the transmission lines to, why? Because those directional couplers and transmission lines to provide the adjustable phase shift, TDL phase shift. I told you we need this particular phase shift in the TDL. So the TDL input will be phase shifts. Those correct phase shifts will be given by the couplers and transmission lines. Taking as the input those phase shift, TDL will compensate those phase shift errors, which is there for lower frequency and the higher frequency. In that way, we can compensate those phase frequency dependency, and we can generate multiple beams at the desired direction. So these are the about the narrow band beamforming and the wide band beamforming. Next is the switched beamforming and adaptive beamforming. What about that? In switched beamforming, the receiver choose from any of the predefined patterns in order to enhance the received signals. That means if you see the first diagram, there's the antenna is there, lot of beams, there's a main beam is there, okay, there are other side lobes are there. So this is user one, you can see that. So user one, and this is predefined, that means this, so we cannot change this beam, okay, this is the predefined, and user will, maybe this is, suppose this is 0 degree tilt means the how in which direction the beam is getting tilted. So this is at a 0 degree tilt, maybe my predefined beam, main beam is at 10 degree tilt, that may happen, but whatever there is predefined by the antenna system, and the user will select that particular, that predefined main lobe. But whenever this main lobes will be there, which will be selected by the user, the other side lobes will be there, right? So interference will come. But if you see the interfere 1, interfere 2, so this disturbance will be there in the switched beam scheme. But what is happening in adaptive? When in adaptive array system or adaptive beam forming, the antenna system is smart enough to direct the main beam towards the pilot signal. Pilot signal nothing but means the main users, while suppressing the antenna pattern in the direction of the interference. That means automatically side lobe suppressions will be there, okay, and it will be steered in such a way, in a smart way, that wherever the user is there, whether is at maybe at 30 degree, at 45 degree, or at 60 degree, wherever is there, the main beam will be directed. The algorithm has been designed in such a way that, or the system has been designed in such a way that this main beam will be focused to particular that user, and you can see that this those other interferences or interfere 1, interfere 2, they will get the null. And obviously if they will get those nulls, then there will be no interference in the user 1, okay. So that is called adaptive array systems. The main beam will be directed towards the user or the pilot signals, and the other interferer will get the nulls. The antenna will suppress those interference signals. They have to suppress the other antenna patterns, other side lobes, so that I can reduce my interference. So that is the difference between switched beam forming and the adaptive beam forming. Now, if we compare the switched beam forming and adaptive beam forming, just like a side by side, in terms of coverage and capacity, so obviously better coverage and capacity is there for the better coverage capacity compared to conventional antenna system. That means conventional means there is no beam forming is there in the previous technology, where not very conventional system is there. From there, obviously, in switch beam forming, the coverage and capacity has been increased from 20% to 200%. But if you compare from the switched beam to adaptive beam is more advantageous compared to switched beam. It is giving more coverage and capacity. In terms of interference elimination, already I have told you the suffering from problem of differentiating between the desired signal and the interference signal. if you go with the switch beam forming, very difficult to differentiate which one is the desired signal, which one is the interference signal. Because suppose here also one main user is there, here also two other another users are there. So which one is the main user, which is having, which needs the more radiation or more signal? So they will get confused in the switch beam array. But in adaptive array, as it is smart enough, that's what it is also known as the smart antenna systems. So offering more comprehensive interference. The interference will be less because that interferer will get the nulls from the radiation pattern. So I can reject my interferences. But yes, but in terms of complexity and cost, obviously the Swiss beam forming is more simpler, and also because we are using simple algorithms, the mechanical point of view or that the infrastructure point of view, it is much simpler. Whereas the adaptive beamforming is much complex, much costlier, because because it's like smart antenna system, and we are going to use very much complex algorithms. So next is that small cells. Okay. Now what is small cells? Small cells is nothing but the base station. It is not different from base station. Base station we can also call it as small cell, or small cell can be also called it as a base station. So there's a, if you assume the small cell is a big umbrella. Okay. So under this big umbrella of small cell, these are, so there are a lot of other cells are there, which are known as macro cells, micro cells, pico cells, and femto cells. So these are the four cells are there which comes under this small cell or base station. So why these classifications are there? For different applications, different coverage requirement, different capacity requirement. So these are the different cells are there. So macro cell is also a small cell, femto cell is also a small cell. So if you see that there is a table that macro cell. So it's a macro cell consumes very huge power. Okay, output power is 10 to 50 watt. But obviously it can cover more distance. You can see the cell radius is 8 to 30 kilometers. It can cover using a macro cell. Users, it can give the access to more than 2,000 users. It's one single macro cell, and mainly it's for the outdoor applications. Okay, obviously macro cells, you know that macro cells deployed in the outdoor scenario. Okay, generally in the village side. Okay, in the urban area, rural area, we put the best macro small cells or macro base station. Next is that micro cells. Power has been reduced, consuming power has been reduced 1 to 10. Obviously, my radius has been reduced, cell radius, coverage radius has been reduced 0.2 to 2 kilometer. Users is around 100 to 2000, between 100 to 2000. And sometimes micro cells can be used in indoor or outdoor. So micro cells and pico cells, these can be either used as indoor and outdoor depending on that how many users you like to have, you like to give the access, or how much distance you want to cover. Depending upon that, you can use micro cells or pico cells in indoor or outdoor. Next is the femtoscales. Femtoscale is is having very less power, very, and it's only purely for indoor, generally for home appliances, for home applications. Maximum it can go up to office, some small offices. These femtoscells are used purely on indoor. So all comes under the same category. This is called small cells. Okay. Now, as I told you that use cases, what is the deployment scenario of the small cell radius? So generally, for the, if you say the outdoor, I told you that carrier outdoor means the downtown area, at the street level. There we can use the macro cells. If I call it carrier indoor, okay, carrier indoor, that means malls, stadiums, not purely indoor, carrier indoor like semi indoor kind of thing. Malls, stadiums, train stations. There we can use the either micro cells or picocells, right? Here, the second and third, picocells and microcells. Next, for the enterprise, like for that industrial manufacturing sites, private electric networks, where like data security is also important. There also you can use the picocells or microcells. And also, and only for the household or small neighborhood, we can use this femtocells. And nowadays, like if you see that these are like result published in North America by Small Cell Forecast, the people like or the requirement is more in that career indoor nowadays. Okay, 55% people are using for the career indoor applications, the small cells. 30% are using in the career outdoor. Enterprise and the for femto is very less, like around 5% to 10%. Also, throughout the year, also it has been shown that how this usages of career indoor has been increased. Okay, and day by day, this career outdoor and indoor both will be too similar. Maybe in 2024, you can see that career indoor application has been more, but career outdoor is also like it is also increased, but it is increased slowly. Mostly career indoor, that is malls, stadiums, train stations, office premises. So more and more we're using the this micro cells or the pico cells. Next, as a manufacturer point of view, what are the challenges to have the small cell radios? Right. The main thing is that the small size and weight. So we have to be very much assured that our small cell product should have small size and weight. Why? Generally, it has been recommended small for to deploy any small cells. We should not like create a different tower. Generally, previously for LT, whenever a tower is required, a big tower we deploy, right? Big base station antennas, big cells, big tower is there. But small cell concept is a little bit different in that point. Small cell will be installed or will be deployed in the existing systems. Just for example, you can see that there's a light post is there, right? If I need to deploy small cells, that may be micro cells or pico cell, whatever, I don't need to put a separate tower for this. I'll just take my device, I'll put it with this in the side of this light post. So obviously, size, I have the size constraint. I cannot have a very big devices which cannot be fitted in the existing model. So small size and weight should be you have to keep in mind while designing the small cells. High reliability and robustness. Reliability because generally small cells have been introduced to access or to give the access to the high data traffic area. So if suppose if a cafeteria, if in an office premises, is my small cell is not performing all well, or small cell performance goes down, you can imagine how much chaos will be created, right? So it should be the design should be in such a way that it should be highly reliable. The small cells, power efficiency. Next, this power efficient it should have very much power efficiency. We cannot like power consumption should be very much less. That is also another point as a manufacturer point of view. And time to market. Market means how fast you can fabric you can manufacture one small cell, because there are a lot of companies out there which are manufacturing the small cells. So how efficiently having the small size and weight, having the highly reliable device with high power efficient, and how quickly you can bring your product to the market, that is a also very challenging thing. So these are 4 points we need to keep in mind as a designer point of view, as a manufacturer point of view, that to while designing the small cells, these 4 points should be we should keep in our mind. Next thing is the manufacturer challenges regarding RF point of view. Okay, these are about that like kind of broad point. Now, in designing point of view, what are the challenges that there in small cells in RF point of view? So first challenge is that increase number of bands, because I told you that 5G in very initial, I was talking about that 5G is not a separate technology. We have increased the number of bands in LT. So obviously, when we have increased the number of bands, that is the issue, because we have to accommodate all the bands, right? Because we need to devise such a system which can be accessible in all the regions throughout the globe, right? So obviously my number of bands has been increased. So full portfolio of the front end products, what will be the my front end products that should have the capability for covering all the regions and all the brand bands, including the sub-6 gigahertz. Next is that increase bandwidth and increase radio capacity. Whenever I am increasing the bandwidth, obviously my radio capacity will be increased. Fine, that is okay. Bandwidth increase, radio capacity will be increased. But along with that, There is also problem with the PAs and LNAs, the power amplifiers and the low noise amplifiers, which are also is the subset or the part of this small cell radio. Because those PAs and LNAs should also have the capability to cover the wide band, and it is very difficult to design such a PA and LNA. Okay, having this wider bandwidth, maintaining the linearity performance. Maybe we can have a wider bandwidth PA and LNA, but linearity maintaining with this bandwidth performance is very difficult. So the choosing of such PA and LNA with the wider bandwidth performance is also a very difficult task. Okay. Next is that as we have coexistence between bands, a lot of bands are there, and each bands to another band is separated. So we need to have a proper coexistence between bands, and how we can achieve that with the BAW filter, bulk acoustic wave filters. Using the BAW filtering, we can have a better band separation or band isolation. Okay. Now, whenever you have a better isolation, obviously my performance will be more. So BAW filtering is the technique which we generally use for the small cell radios to have a better isolation from band to band, intra-band isolation. Now, I should have a highly power scalable PA, because I am increasing with the like 3 dB increase. If we increase the 3 dB power in the small cells, so power scalable should be there. So my PA should be efficient so that I can have this 3 dB scalable power. Okay. Now, this swap, SWAP. This is very funny word for in our point of view, as a designer point of view, as a manufacturer point of view. That swap is that what? Size, weight, reduce size, weight, and power consumptions. This is the like motto of designing a many small cell, okay, or any antenna, whatever you can call. So this you have to have a reduced size, weight, and power. So this is a very like mantra while designing that a small cell. And to achieve this one, we need a power amplifier with high gain, power added efficiency PAE in a small form factor. DPD, digital P distortion, should have low. DPD means, as I'm talking about the linearity, that we should have a linear performance. So that is coming from the DPD, and also the gain controlling point of view in the LNA. So these are the points which are challenging point. That is another point of view. This high PLA, high PAE with the P8 and controllable DPD and controllable gain for the LNA. So, in conclusion, as I discussed with that 5G is a sustainable, satisfied requirement for the 100,000 times traffic growth. It can have that capability to sustain 1,000 times traffic growth, and 5G can provide users with like zero latency user experience, and is capable of connecting 100 billion devices day by day. And also, we are increasing the technology so that it can capable to connecting more and more devices with these different beamforming techniques and with the machine MIMO. And also 5G can deliver a consistent experience across a variety of scenarios, including the case of ultra high traffic volume density, like in coverage point of view, in a capacitive density, high density point of view, with the and high mobility, ultra high mobility. And 5G is also provide to intelligent optimization based service and user awareness. Means I told you like we can have a smart adaptive array systems, smart beamforming techniques that can be also deployed in the we're using in 5G. So there are a lot of intelligent optimizations are there, so that we can generate proper spectral efficiency with those algorithms. And we should also reduce while designing such complex algorithms or complex device, cost is also like it has to be cost efficient. So as a whole, the vision, if you see the vision of 5G, information is a finger away, everything in touch. Whenever you can touch, information should be in a finger away. That is the like future vision of 5G or 6G. Thank you. Thanks for giving the time listening the topic.
Thank you, sir. Thank you for the session. Hello.
Yeah, hello. Am I audible?
Sir, yes. Thank you for the session.
Yeah.
Dear participants, if you have any doubts, you can ask the resource person.
छोटे छोटा नहीं पता लग रहे मम्मा कहते कि ये बड़े बड़े पे बच्चे छोटे भी हैं इन्होंने तो हम दस दिन भी कही
Hello.
निकली आई को छोटा
If you have any doubts, you can ask the resource person.
ever that.
Okay, sir. Once again, it was a very informative session.
Yeah.
A wholehearted thanks on behalf of the Department of ECE MITS.
Yeah.
Thank you, sir.
Thank you. Thank you. Thank you.
Dear participants, we will wind up the session by this. So we will start with the tomorrow on VLSA and nano devices. So with this, the day is completed with all the sessions. Thank you for participating.